Okay, so welcome everybody to the Quantum Machine Learning Meetup, QML Meetup. Thank you so much for joining us again, and thanks for also accommodating the new day, Friday instead of Thursday. And as always, I just want to remind you of where this QML Meetup was created, and what inspired it was really this quantum open source foundation. So if it's your first time looking at things quantum computing, please go and check out QOSF. They're really doing amazing things. There's really nice resources, Slack channel, and a community that you can join that would help you if you are new, or even if you're not new and you're just looking for assistance. So Arusa, Antal, and myself met there through their mentorship program, and we realized how many people were interested in quantum machine learning. And so we thought we should do something about that, and hence this meetup. So this wouldn't be possible as well. I must just make mention of Francesco Petroccioni from University of KwaZulu-Natal and the NETEX colloquium, or how do I call them? The NETEX group, or in National Institute for Theoretical Computational Sciences. And yes, they give us the Zoom license and allow us to host these meetups for us to promote and showcase research in quantum machine learning. So with that, I would like to introduce our speaker, who you all know by now. So it's going to be Marco, who's talking to us about Barren Plateaus and overparametrization in quantum neural networks. And Marco is a scientist at the Los Alamos National Lab, and he does a lot of cool stuff in quantum computing, quantum machine learning, and especially around Barren Plateaus. And Arusa was just saying that they are producing research at a pace that we can't even catch up with, right? So it's the group is doing amazing stuff, and we're very excited to hear from him. And just while I have you, I want to also just make mention that the next meetup will be in January. So we will skip December because most people will be on holiday. So 13th of January, you can mark your calendars, and our next speaker will be Kathleen, and she'll be talking about error-mitigated, data-driven circuit learning on noisy quantum hardware. So cool. And then Marco, you can go ahead and share. Thanks so much again for coming here. And let me stop sharing now. Okay.
All right. Let me know if you can see my full screen now. Does that look good?
Yes. Yes, we see it.
Fantastic. Well, thanks again for inviting me and giving me this opportunity to share some of our work with your community. We're really happy to have this opportunity. And again, thanks to the organizers, and thanks to everyone in Europe that I know it's a Friday, it's 7 p.m. I know that people are probably starting to think about the weekend, so I'm going to try to make this entertaining for everyone and make it worth your time. So today I'm mainly going to be focusing on two different papers, the ones that are here on the slide: diagnosing Barren plateaus with tools from quantum optimal control, and the theory of overparametrization in quantum neural networks. So this is going to be the outline of the talk. Let's see if it works. There it is. I'm going to give a very brief introduction to parametrized quantum circuits and quantum neural networks in near-term quantum computing, why we care about them. I expect that a lot of people here will have some background in QML, so I'm going to try to be brief. Then I'm going to give an even briefer introduction to the theory of quantum optimal control, just to give you the general feel of why we imported tools from quantum optimal control into studying quantum neural networks. Then we're going to study Barren plateaus in certain types of, what we call periodic quantum neural networks, but as we're going to see, they're pretty general. They cover the famous or infamous hardware efficient ansatz, the QAOA ansatz, HVA, and so on. And finally, I'm going to finish with some of our results of overparametrization. So first, let's start with the basic. What is a quantum neural network? Well, let's just start with the classical case. So classical neural networks, as we know, have impacted many areas of science. And of course, the hope is that with the development of near-term quantum computers, we want to try to use this computational model and sort of embed it with the framework of quantum machine learning, in the hope that we can develop what we call quantum neural networks to try to harness the power of quantum computers and outperform their classical counterparts on machine learning tasks. For me, this is especially relevant whenever we're working with quantum data or tasks that are inherently quantum in nature. So whenever we ask the question, so what is specifically a quantum neural network? Of course, the unfortunate truth is that there is not something that we can point towards and say this is a quantum neural network, but we can give a simple definition. It's just a computational model that generalizes the concept of classical neural networks based on the principles of quantum mechanics And there's not one single realization that we can say this is a quantum neural network. There's multiple out there in the literature. We're going to focus on some of them. And specifically, we're going to focus on the ones that we call just parametrized quantum circuits. So this is like the general framework that we're going to be working on. Those can be more general, but we're just going to focus on the ones that are essentially represented by a parametrized quantum circuit. So the general framework for using a quantum neural network, be it in a variational quantum algorithm or in quantum machine learning, is that we have some problem that we want to try to solve. And usually this problem is going to be encoded into an optimization task. So that say that, I don't know, we want to find the solution of a linear system problem with a quantum computer, or we want to do some classification of data using a quantum computer. That data can be classical. We can try to do classification of, cats and dogs pictures, or we can also try to do classification of quantum data. Say I give you a state and you want to know if it's superconducting or not superconducting, and you want to train a neural network for this task, right? So we're going to embed this into an optimization problem. The input to our algorithm is usually going to be given in the form of some training data that we might have for a machine learning task. We're going to define a cost or loss function that encodes the problem in itself. And the goal is to try to find the minima of this cost function as it should represent the solution to our problem. And then, of course, we're going to have some way in which we're going to write this parametrized quantum circuit, which we call the ansatz. And we're going to be working in this hybrid computational model where we're going to have a quantum computer. The hope here is that by accessing the exponentially large space dimension of the Hilbert space, we can solve some machine learning task that classical computers will not be able to solve, or maybe we can solve it more efficiently. And usually what we're going to have is some quantum states that we're going to send through a parametrized quantum circuits. We're going to make measurements out of the states that are coming out of this quantum neural network. And we're going to use those measurement results to try to compute the cost or loss function. This usually defines a hypersurface, which we call the landscape, the cost function or loss function landscape. And the goal is to try to navigate the landscape to try to find the global minima. How do we do this? We usually leverage the power of classical optimizers in classical computers, that we feed them the value of the cost function, maybe also of its gradients, and it's going to give us a new set of parameters that we're going to put into our quantum circuit, and we're going to repeat this loop until some convergence has been achieved. The output of the algorithm depends on the problem that we're trying to solve. If we're trying to do some BQE, it might be a quantum state, maybe the ground state of a molecule. We might also be looking for a probability distribution if we're doing some generative model. But generally speaking, what we're going to care for here is what's happening in this part here. This is, the more typical representation of the quantum neural network, but typically of a classical neural network, but typically it's going to be a parametrized quantum circuit for us. So, of course, here, let me just briefly make this comment about variational quantum algorithms and quantum machine learning. Those are two different things that we've been working on. And, at one point, I remember I ran a Twitter poll and I was saying, are variational quantum algorithms quantum machine learning schemes? And there was like a big division in the community. So I think that there are some difference between the two, between what we call variational quantum algorithms and quantum machine learning. So of course, this is the typical variational quantum algorithm from the VQE paper. And what we're going to have is, usually the input to this algorithm is going to be an easy to prepare state. It might be the old zero state, or maybe some mean field solution to a quantum chemistry problem. We're usually not going to be dealing with training data. This is why I don't really consider this quantum machine learning. This is more task-oriented programming. And, the goal is, again, to minimize a loss function, which is going to be a linear expectation value. Oh, here I'm missing an H, by the expectation value over some Hamiltonian. And the goal is, of course, that we want to train this parametrized quantum circuit. In quantum machine learning, be it with classical data or quantum data, we're going to be usually dealing with non-trivial states that are going to go into my quantum neural network. Those can be, again, like ground states of some problem that I want to classify, or some classical data that has been encoded into quantum states. We're going to minimize loss functions that are usually nonlinear. So whenever I talk about cost, I'm going to refer to something that is linear, loss something nonlinear. But of course, here we also train a parametrized quantum circuit. So in the timeline of why do we care about training parametrized quantum circuit, we can think about what we expect for quantum computers. Right now, we are at the noisy NISQ era, where we have, limited number of qubits, limited depth, because of the number, because the noise eventually will limit how much we can do. We expect that at some point we're going to have partial error correction and eventually fault tolerant error correction. So VQAs have been envisioned to work in the NISQ era. There will have some partial overcorrection use whenever we're going to be able to implement higher fidelity circuits, and they're used in the fault tolerant era. It's still under discussion. I believe that they will be useful. We can still use all of those qubits that we're going to have to run very large variational algorithms. But of course, quantum machine learning, the way that I see it, is always going to be useful. Now, in the near term, for making practical use of NISQ devices, but also in the fault-tolerant era, because there we're going to be able to efficiently and with high accuracy prepare quantum states, and we're still going to want to do information processing tasks on those quantum states. So, training a quantum neural network is something that we expect is going to be useful, not just in the near term, but also in the long term. So understanding the trainability of quantum neural networks is going to be fundamental. So why is it important to us to analyze the trainability of quantum neural networks? So here, if we go back again to the classical and we do a little bit of history, despite the wide use of classical neural networks, they've seen periods of great stagnation, or what was called winters. First the single perceptron was devised, then it was realized that multi-layer perceptions were more powerful, but harder to train. The backpropagation method was developed. But throughout all of these times, there were periods where it wasn't really sure what was the use of neural networks or what was the scope of their power. So of course, for us, the question is, are we heading somehow into a quantum neural network that we're not yet envisioning? Or if we are, how can we try to avoid it and prevent it? And here the question is that, why specifically trainability? Well, because in VQAs, we usually care about the solution quality. Here, VQA is variational quantum algorithms. And that usually depends on how well we can train the parameters. In QML, we care about generalization errors, not so much about training errors, but mostly about generalization error. But they, in turn, also depend on how well we can train our parameters. So training quantum neural networks is going to be fundamental for making practical use of quantum computers. And understanding the trainability of quantum neural networks is extremely useful to try to prevent winters and sort of guarantee that we're not, that quantum neural networks could outperform classical neural networks. So how do we analyze the trainability of quantum neural networks? Here we go into what we call quantum landscape theory. This is a term that we're trying to install and to use to try to, and what we mean by it is, the quantum landscape theory is going to be the study of properties of VQA cost functions, or QML loss functions landscapes. And what we want to try to analyze is how those landscapes emerge and what are the properties that they have that can affect the optimization process. So, there's several features of a quantum neural network that is going to affect its trainability and also its practical usefulness. So there's many things that one has to keep into consideration whenever you're developing a quantum neural network. For instance, the first is, again, this ansatz, what we can call by what, when, and why gates. What gates are we going to be using? When are we going to be placing them in the quantum circuit? Why are we placing them where we're placing them? And of course, here there's many things that come into play. We can have the so-called unstructured ansatzes, where we follow some sort of like connectivity in our device to try to reduce the depth. But we can also try to build ansatzes that have information about the problem embedded into it, so that we can try to explore more relevant solutions, relevant space while we vary our parameters. And of course, here, the main goal is that we want to try to guarantee that a solution actually exists within a set of parameters. But even if we know that the solution exists, there still could be some issues. For instance, maybe we can have Barren Plateaus, and that means that whenever I initialize my optimization, the first iteration of my optimization, am I going to be able to find a cost minimizing direction and train? And even if I train, how do I know that I can actually get to the global minima? How do I know that I'm not going to get stuck in a local minima? So there are multiple issues that one has to deal with. Mostly some of the study that we have been doing has been around Barren Plateaus. But as we're going to see here, whenever we talk about overparametrization, now we're starting to analyze a little bit more. Let's assume that we don't have a Barren Plateau. We can start moving in some minimizing direction. Well, how many local minima do we have? How can we guarantee that we're going to be able to find the global minima? And of course, there's more things that we care about here. Maybe we also care about noise robustness. We can care about efficiency. Efficiency is going to be key throughout this talk. And why do I mean by efficiency? I mean that I want to keep all of the scaling in my algorithms polynomial with the problem size. Because if I have an algorithm that scales exponentially with the system size, it's not going to be better than any classical algorithm, right? And I'm not going to have any hope of achieving a quantum advantage. And then why am I using a quantum computer for a task? So here we want to keep the number of shots polynomial in the system size, the number of parameters polynomial in the system size, because those are the sort of algorithms where we can expect a quantum advantage to arise in. So first, let me give you one slide quantum optimal control crash course. I am by no means an expert in quantum optimal control. This is part of the work that my collaborators have done. So I'm going to also try to be brief for the sake of not messing this up. So quantum optimal control is a theoretical framework that provides tools for the systematic manipulation of dynamical quantum systems. And here the main idea is that you have some quantum state and, it's going to evolve under some Hamiltonian of the natural interactions of that quantum state. And after a given time, it can evolve under the evolution of H0 and get to some quantum state. But of course, the thing is that maybe we want to take this evolution, but we don't want to let it evolve just under the natural evolutions. Maybe we want to try to get to some state that is of interest to us. So quantum optimal control, what it does is try to control the evolution. And the way that it does this is that the evolution now, it's not just going to be governed by the internal interactions, but also by external. In this case, usually it's going to be fields that we're going to be applying to our quantum states. We're going to interact with it to try to control its evolution. And this evolution is usually going to be characterized by some control fields that we have to try to fine tune to get to the final state that we want to get. And usually what happens here is that we parametrize the control fields and we define a cost function that defines that is going to tell me what's the state that I want to try to get to. And we're going to train the parameters to try to minimize this cost function. Now, of course, at this point, if this sounds very familiar to what we were discussing in variational quantum algorithms and quantum machine learning, it's because it is. And variational quantum algorithms and quantum optimal control can be seen as two different facets of the same optimization problem. In variational quantum algorithms, we usually have a system that is made out of qubits. And what we're going to do is that we're going to apply quantum gates that are going to make our system evolve. We're going to take measurements and again, optimize the parameters with some classical optimizer. Well, quantum control is essentially the same thing at a different level. Instead of being at a gate level, we can think about it as a pulse level. So one level above. And what we have here is we're going to apply pulses rather than quantum gates that are going to be interacting for a given time. And we're going to make our state evolve. We're going to take measurements. And again, we're going to feed those to a classical optimizer that is going to tell us what the next step should be, update the controls. And this first realization was done in this beautiful paper by Alicia McGann and company. And it's a great read. I highly recommend it. So the next aspect that we want to ask here, and this is one of the main questions in quantum optimal control, and of course for us too in quantum neural networks, is given a quantum optimal control system or a quantum neural network, what is the set of possible states that I can reach? How do we characterize, if I start in a given state, where am I going to be able to end up after some evolution time? And of course, here you can think about it either from a control perspective of quantum neural net or quantum neural network. This is completely agnostic. What we're going to have is some initial quantum state. For quantum neural networks, we can give the different sets of parameters that are going to generate different unitaries that are going to take us different places, right? So we can think about families of parameters. Give me families of unitaries that represent the action of the quantum neural network, and that is families of output states of my quantum neural network. And you can already see that if we're trying to get a given quantum state at the end, or a quantum state that minimizes some expectation value, then trying to characterize everything that is happening here is going to be fundamental. So in quantum optimal control, what people do is that they're going to define the set of generators that define the evolution of the system. So here, those HKs, you can think about what is the set of generators that generate the evolution in my quantum circuit, or the same as in quantum optimal control, the fields that I'm applying to the system. With that, what people do is compute the Lie algebra that is obtained by the nested commutators of the operators from the set of generators. And from here, what you do is that once you've managed to find the basis obtained by just doing all of this set of generators, eventually the algebra is going to be closed under commutators. And what you're going to get is this Lie algebra. from the Lie algebra, we can define the Lie group, which is just essentially the set of reachable unitaries that you're going to get by exponentiating the set of generators. And here, finally, we can characterize the set of reachable states by just applying elements of the Lie group to my initial states. So altogether, this is going to be very important throughout the rest of the talk, because we're going to be doing an algebraic analysis of the properties of quantum neural networks. So the most fundamental quantity that we have here is this Lie algebra, because this is going to be at the heart of the rest of the evolution, of the rest of the characterization. The Lie algebra defines the unitaries, which in turn define the set of reachable states. So the message usually in control is the bigger the Lie algebra or the Lie group, here we can actually change this for lowercase g, the more expressible the control system. So that means that we can generate more unitaries, more states that I can reach. And in quantum optimal control, there's this thing that people study, which actually people look forward to, which are controllable systems. That is the case whenever the Lie group is just essentially all the unitaries that you can possibly generate. And in this case, it's been shown that, you know, the optimization landscapes for quantum optimal control have some really nice properties in the limit of very large evolution, or, you know, infinite number of parameters, like you have quasi-convex landscapes, or your evolutions are possible. So this is something that people in control theory have studied. Now, of course, what we want to do is try to import those tools for analyzing the loss landscapes. And you can see here that the connection between or how the Lie algebra is going to appear is going to be very fundamental, because what is, at the end of the day, you know, the set of mathematical spaces that are going to be relevant whenever we're analyzing our loss landscapes. So first, we have a set of parameters in some parameter space. What we're going to do with them is put them into our quantum circuit that is going to give us unitaries. So we're going to have now unitaries in the unitary space. And again, as we said, those are going to be eventually generated by the Lie algebra, are going to be spanned by the Lie algebra and the Lie group. And then we're going to apply those to quantum states. And by making measurements on those quantum states, we're going to be able to get to characterize the loss landscape. So again, here we can see how they're going to be playing a role. And again, also to make a comment that the Lie algebra is going to appear at a higher level of abstraction than the loss functions, because it's still not taking into account how the loss function is defined, right? It's just taking into account what is the set of states that I can reach by sending states through my quantum neural network. So again, this is just repeating a little bit what I just said. I'm just going to quickly jump over this. And for the case of what we're saying in quantum optimal control, we call this like the dynamical Lie algebra. So we can again start to see why in quantum neural networks, this is going to play a very important role. So, you know, this was like almost a 20-minute background section. I'm going to try to jump to some of the interesting results. So first, I'm going to start with Barren Plateaus. So this is a slide that maybe some of you have seen in some of my other talks, but it's just to say that Barren Plateaus are an issue in quantum machine learning because of precision, because quantum computers are probabilistic in nature. And this is a fundamental issue with Barren Plateaus. Because, for instance, if I give you a question, given a 1-qubit state, you want to estimate the probability of this qubit being on the all 0 state. For a theorist like myself, the solution is very easy. Just take my quantum state, projecting to 0, and that is the probability of the state being a 0. In practice, this is not how it works. If you have your quantum state row in a quantum computer, what you have to do is measure in the computational basis a bunch of times, a big N number of times. You check how many of those results were on 0, and you do this fraction right here, and that's going to be, you know, your statistical estimation of what this probability here is going to be. And with basic statistical theory, we know that this has an estimate of the order, this has an imprecision of the order of 1 over the square root of n. That means that the more measurement shots we take, the more of our precise estimate is going to be with this fraction right here. So, you know, let me give you a non-mathematical definition of Barren Plateaus, which is that in average, the cost function partial derivatives become exponentially concentrated around 0. And that usually means that we have an exponentially flat landscape. It has some slope, of course it has, but it's exponentially hard to find it, right? There is going to be some cost minimizing direction, but we need many shots to find it. So for instance, we can think about some optimization process. It might use gradients. It might be just trying to compare 2 different points in the landscape to see which one is slightly below the other to take a step in that direction, like an Elder-Mead gradient-free optimization method. And now let's say that, those gradients or those cost function differences are of the order 1/2 to the n, as we said. So for 4 qubits, that means that our gradients are about 0.06. And if we have a statistical precision of 1/√² of n, that means that we're going to need about 256 shots in my quantum computer to estimate what this cost minimizing direction is. Of course, if we have 20 qubits, now those gradients are, 9.5 times 10 to the minus 7, and we need 1.1 times 10 to the 12 shots. That is 1 trillion shots just to be able to estimate for one parameter, what is the direction that I should be taking a step on. And of course, here, something very important to mention is that Barren Plateaus are not characterized by the expectation value of my partial derivative being 0. This is actually fairly common in landscapes, even whenever you don't have a Barren Plateau. It's just telling you that, your landscape is not tilted. I don't have any preferred direction. The characterization of the Barren Plateaus has to be through the variance of the partial derivatives. And this is how you will usually check and see Barren Plateau results in the literature. So Barren Plateaus have been greatly studied, and just to give you this sort of picture of what happens if I don't have enough shots. So in a landscape with no Barren Plateaus, I initialize, I'm going to be able to do an efficient number of shots, find a cost minimizing direction, hopefully get to the global minima. In a Barren Plateau, what's going to happen is that if I don't have enough shots to say which is the direction that I'm going to be walking in, the statistical precision or that statistical noise that I'm going to have is going to be the one dictating the direction that I should be walking on. And I end up with just essentially a random walk. And Barren Plateaus have been shown to arise for global measurements, noise, deep circuits, or the expressibility of the circuit, by entanglement that you're generating in your quantum neural network. And most of the work in Barren Plateaus has been done for the hardware efficient ansatz. And this is reasonable. This is an ansatz that is still widely used because it's problem agnostic, it reduces the gate overhead, and most of the proofs rely on the gates being local to designs. But of course, one of the things that people say is that hardware efficient ansatz, they should not be used. It's like trying to have one algorithm to solve all the problems. We sort of expect that this is not going to happen because of some, sort of like no free lunch result, that there's not one hammer for all the nails. So maybe we shouldn't use hardware efficient ansatzes. Maybe we should use what people call the problem inspired ansatzes or structured ansatzes, because maybe those can avoid Barren Plateaus. And it was largely believed that those would actually avoid Barren Plateaus. So now let's get into some of our results. Here we consider periodic structure ansatzes. So we're going to consider quantum neural networks, which are going to be of this form. So you see here that what we're going to have is a set of unitaries that are going to repeat themselves, generated by HK, and those are going to define one layer. And then I'm going to repeat this multiple times. Oh, again, another typo, sorry, this should be uppercase L. And we're going to repeat the structure big L times. So you can naturally see that here this sort of fits within the framework that we're previously analyzing. We're going to find the set of generators and the ensuing dynamical Lie algebra as the one obtained from this set of generators. And interestingly enough, this sort of ansatzes are quite general, and they include a wide range of ansatzes that are used in the literature. Specifically, already the hardware efficient ansatz, we get it for free, but it also includes the Quantum Alternating Operator Ansatz, the Hamiltonian Variational Ansatz, Quantum Controlled Inspired Ansatz, and many others. They will usually have sort of this periodic structure to them. Now, how do we study Barren Plateaus? So, as we said, we're going to study the dynamical Lie algebra. And the dynamical Lie algebra, it can, whenever you compute it, there's multiple results that you can say. We already talked about controllable, but there's many different cases of study that are of interest. But let me just quickly summarize some of the results that we got. For instance, our first result is that whenever your system is controllable, that means that you can generate all the unitaries, your system will exhibit a Barren Plateau. This is, of course, something that we can expect because your system is completely expressible. You can generate any unitary. This is a case, for instance, for the hardware efficient ansatz. Wherever I have like local rotations and local CNOTs, this is going to have a Barren Plateau. We already know this, but we can recover this result from a controllable perspective. Then we can also see, for instance, if you're trying to do QAOA for a spin glass, it's also going to have a Barren Plateau. So this provides like a no-go theorem for trying to use Hamiltonian Variational Ansatz and try to solve a spin glass with this, because it's going to have a Barren Plateau. This follows from the fact that controllable ansatz will form two designs, and it gives us this really nice perspective of quantum optimal control, because remember, as I said, controllable systems, they have quasi-convex landscapes, and people really like them because they say, I can always start in some point in the landscape, walk in a straight line and get to the minima. This is actually true in a Barren Plateau. I can start here, walk in a straight line, get to the minima. There is no features in the way that will prevent me to get here. Of course, this is not practically useful because I need an exponential number of shots. So this also gives us a new perspective to bring back into quantum optimal control and to sort of inform the quantum optimal control about how some of the results that they have also a counterpart to them. Like, sure, this is great, but it's not going to be practically useful. You know, we can also study the case wherever your system has symmetries, so it cannot longer be controllable because now your Hilbert space is going to be split into a direct sum. And for instance, this happens, for instance, in the XXZ Hamiltonian, you have magnetization symmetry, and your Hamiltonian is going to be block diagonal. Your unitaries that are generated from the set of generators are going to be block diagonal. And here, the results that we get for the variance of the cost function partial derivative is that they actually depend on the dimension of the subspace that my state belongs to. So that means that if I send a state that belongs in a small subspace, I might not have a Barren Plateau. But if I send a state that belongs to an exponentially large subspace, I will have a Barren Plateau for exactly the same ansatz. So this is the first time that we see how the input state can actually determine the trainability of your system. If you're sending a state that belongs to a subspace, a symmetric subspace of your ansatz, that could be really bad because now you're again exploring a very large space. And you know, maybe our more important result is that we can link the variance of cost function partial derivatives with the dimension of the dynamical Lie algebra. This is at this point an observation. We're still trying to formally derive this, but this has been already independently verified in other problems. And what's really nice about this is that usually the way that you diagnose Barren Plateaus is you have to go and compute this variance of the partial derivative. This requires one, thorough theoretical analysis of your ansatz, like trying to see what happens whenever I start changing my parameters, or it requires numerics. And those numerics become very expensive whenever you're trying to see the scaling of that variance for large problem sizes. If we use this method, you can see that all that we have to do is compute the algebra, compute the dimension, and if this dimension is polynomial, then we already know that our variance is going to be polynomially vanishing. If this dimension is exponential, then we know that our variance is going to be exponentially vanishing. And the thing about computing the algebra is that this is completely classical. We do not need a quantum computer to estimate the dimension of the Lie algebra. This is all purely classic. So this is a novel method to diagnose Barren Plateaus that doesn't require access to a quantum computer. You just have an ansatz. You want to know if it's going to have a Barren Plateau or not. You can do this preliminary analysis without having to expend precious quantum resources. And for instance, here, we can do some analysis of are ansatzes going to be good or not? Are they going to have Barren Plateaus? For instance, you can have an ansatz that looks like this. This is very much what you would use in QAOA for a simple graph of first neighbor connectivity. And this one has polynomial algebra. But then you can say, sure, or what happens if I make my ansatz slightly more complicated? What happens if I now take this and I just add one extra rotation per layer, and all of those rotations have the same parameter? This would almost seem like an innocuous change that I'm going to do to my ansatz. Maybe it's going to make it a little bit more expressible, and maybe I can reach the solution faster. The problem is that this small change, if you compute the algebra, now is going to make it exponentially large. And what's going to happen is that this one right here is going to have polynomially vanishing gradients. Now this is numerics. And this one right here is going to have exponentially vanishing gradients. So this small change that we wanted to propose to our ansatz, we now know that this is not a good idea because we took a perfectly good usable ansatz and made it completely untrainable. And this observation of the relation between these two, we can actually verify this numerically in a log-log scale. Line means there is a polynomial relationship. So this gets verified numerically. So our work also opens up novel trainability-aware ansatz design strategies, where before doing something like this, you can check if it's going to be a good idea to do it or not, because you might mess up your trainability. So the main message of this part of the work is that problem-inspired ansatzes are definitely not immune to Barren Plateaus. They are going to depend on what is the set of generators. And here we also see, for instance, the role of the input state. Even for a fixed ansatz, I send different input states. I could have Barren Plateau for some of them and not have Barren Plateaus for other of them. And of course, here we highlight the importance of the dynamical Lie algebra and the fact that it can be computed without a quantum computer. And again, just going back to our previous example, be very mindful that simple modification to an ansatz, like I'm just going to add a couple more rotation, that can greatly change your trainability. So whenever we're designing ansatzes for some problem, now we can think about this trainability-aware ansatz design. And for the last 10 minutes, I want to go into the overparametrization phenomenon that we have studied. So here we're going to still focus on the same periodic structure ansatzes, and probably, as some of you might have guessed, we're going to see that the dynamical Lie algebra still plays a very important role in defining overparametrization. So it is definitely a fundamental quantity to keep in mind. So back to classical neural networks for a second. There are some things that we know about classical neural networks. So in some cases, training a generic neural network can be NP hard. It has non-convex optimization landscapes in general. So people have been looking for ways to improve the training and the generalization errors. And one of the ones that they found was the overparametrize your neural network. And here, what this means is that we're going to be using a neural network that has a capacity that is larger than that which is needed to represent the training data, the distribution of the training data. And overparametrizing a quantum neural network has been shown to improve its performance, reduce its training and generalization error, and even lead to provable convergence results. So overparametrization is an extremely powerful tool in classical neural networks. And of course, whenever we go to quantum machine learning and quantum neural networks, we also know that training VQAs can be NP-hard. We also know that it's a non-convex optimization landscape. So the question is, can we also try to get some results which will make our life easier in some cases? And if so, can we overparametrize a quantum neural network? Now, there's been some preliminary results analyzing the overparametrization of quantum neural networks. Most of them are heuristics. They just show that in some cases, you have a more favorable landscape where you can achieve faster convergences, but there wasn't a general theory. So this was our goal. Let's try to define a general theory to take the first step towards analyzing the overparametrization phenomenon in quantum neural networks. So the first thing is we're going to give a definition. So this is our definition, and bear with me for a second. We are going to say that a quantum neural network is overparametrized if it has a number of parameters such that the quantum Fisher information matrices for all the states in the training set saturate their rank. So let me just give you a second to digest this. This means that I have enough parameters that the QFI matrix for each state in my training set, each state that I'm sending through my quantum neural network, has achieved its maximum possible rank. If I increase the number of parameters, that will not increase the rank for the quantum Fisher information matrices. So very quickly, the Fisher information matrix plays an important role whenever you are studying the differential geometry of quantum states. It's related to the Fubini study metric. You can think about it as the first non-trivial order. Whenever I take two quantum states, I just take one, make a small perturbation in the parameters, and I want to see the distance between two quantum states. The quantum Fisher information matrix is going to appear here, and it's essentially telling me its rank is telling me how many independent directions I can move in the state space. So what does this tell us? This overparametrization definition is very mathematical, but what does it tell us about our quantum neural network and about our landscape? So first, we're going to define, small number of parameters is underparametrized, big number of parameters can be overparametrized. And why is this important for landscapes? Because remember what I just told you, the rank of the quantum Fisher information tells us how many independent directions we can move in the state space. So if we have very few parameters, then there means that there are some directions that I cannot access. Because, if I keep increasing parameters, I keep increasing rank, there's more directions. So small number of parameters means that there are some directions that I'm not exploring. And this could be an issue because, for instance, if I have a loss function hyperspace and think about, I here have only one parameter, so I just move along this red line, I can have something that looks like this. And here I can have a local minima that I can get stuck in if I only move along theta1. Now, of course, if I add another parameter, theta2, it could be that now I can explore another direction that I previously wasn't able to explore. So now, instead of exploring a line, I can explore all of this green region right here. And you can see that this blue part that was previously a local minima is actually not a local minima. It's, for instance, a saddle point. So this local minima for just moving on a smaller number of parameters is what we call a fake trap or a spurious local minima that only exists because I'm not able to explore all relevant directions. So whenever the rank of the QFI is saturated, that means I increase number of parameters, I'm already exploring all relevant directions. So in this sense, our definition of overparametrization is sort of linked to a computational phase transition in optimizing my parameters where I'm no longer going to get stuck in fake local minima. Those are not going to be an issue anymore. So here, what we can prove is that the maximum rank of those QFI matrices is bounded by the dimension of the Lie algebra of, which is here, there's a subset S because it's linked to the states of my input state. Now I'm thinking about a collection of states. So I have to look at, if I have symmetries, what is the space that all of those states belong to? What is the symmetric space? But essentially, the dynamical Lie algebra also plays a role here. And what we find is that one can actually achieve overparametrization when the number of parameters is about the dimension of the Lie algebra. So what is this telling us? This is telling us is that I can achieve overparametrization with a poly-sized algebra with only a poly number of parameters. And this is, again, keeping to the efficiency of the ansatz, just not having exponentially scaling. Because if I have exponentially large algebras, like the ones that I get with controllable system, I need exponentially many parameters to be able to get to that quasi-convex, very nice landscape that people like. But again, not only will I have a Barren Plateau, I cannot deal with exponentially many parameters. So here, we will mostly care about poly-sized algebras. So more than that, we can also give overparametrization and operational meaning in terms of the capacity of a quantum neural network. So here, let me recall that the capacity or the power of a quantum neural network quantifies the breadth of functions that it can capture. So I'm going to recall two definitions. One of them is by your very own Amira Abbas, organizer for this talk. And what they show is that in the limit of many qubits, their measure of capacity is given by the rank of the classical Fisher information matrix, the maximum rank that the classical Fisher information matrix can get. There is also another definition by Tobias Wang, Kishore Bharti, and company, that they define it as this quantity right here. If you look at it really for just a second, you're going to realize that these are the eigenvalues of the quantum Fisher information matrix, and this is a function that is 0 if the value is 0, 1 if the value is not 0, or this should be different than 0. And essentially, this is just the rank of the quantum Fisher information matrix. So be it quantum or classical Fisher information, they both appear in capacity measures. So what we have is that the model capacity first is going to be upper bounded by the dimension of my Lie algebra. If I have a poly-sized algebra, that is the maximum that this capacity is going to have. But not only that, we give this operational meaning that an overparametrized quantum neural network means that its capacity is saturated. I keep increasing number of parameters, its capacity is not going to keep going up. So this shows this maybe more intrinsic connection between our notion of overparametrization and how much the quantum neural network can actually capture. So we have this really nice meaning to it. Of course, we also run numerical experiments. This was done by one of our students in this year's quantum computer summer school at Lano for a VQE implementation. We take a system that has a polynomially sized algebra. And what we see is that as we start increasing the number of layers or parameters, this is how close we are to the ground state as a function of iterations. You can see that for both 4, 6, 8, and 10 qubits, for small number of parameters, I cannot reach the solution. That means that there's not a solution that actually exists. But as I start to increase the number of parameters, I am going to have this computational phase transition where my optimization becomes much more favorable because now there's no more fake local minima, and I will be able to reach the global solution exponentially faster, which is really nice. Here you can see that this log linear scale tells me that I'm reaching the global minima exponentially faster. And of course, what we can see here is what is the success probability for given number of layers or given number of parameters. And what we see here for different problem sizes is that the dynamical Lie algebra, again, holds the point in which the computational phase transition exists. I can see here that, for instance, for 10 qubits, I need about 100 parameters. That is the dimension of the Lie algebra. For less parameters, I have very little success probability. As I get here, the jump occurs. And after this, I can still keep increasing the number of parameters and get further improvements, because in different points of the landscape, my rank might not be saturated, until eventually there comes a point where further increasing the number of parameters does not help. I'm in a fully overparameterized quantum neural network. So overparametrization is not a single point, it's actually a transition region. It's like a whole region where your quantum neural network becomes more overparameterized. We have also results showing that the dimension of the Lie algebra bounds the rank of the Hessian at the solution. And we can see here that for both problems that we consider with open and closed, it's just boundary conditions for your ansatz, the dimension of the Lie algebra is going to be an upper bound for both the rank of the quantum Fisher information matrix at different points in the landscape and the Hessian evaluated at our global optima. So that means that our results are verified by the numerics. So to start to wrap this up, the theory of overparametrization in quantum neural networks, we provide the first algebraic theory to study the overparametrization phenomenon within what we call, again, the quantum landscape theory and the quantum landscape perspective. So again, we see that the dynamical Lie algebra obtained from the set of generators is going to play a crucial role in determining properties of the quantum neural network and the ensuing landscape. And the overparametrization phenomena has been shown to greatly simplify the landscape by removing spurious local minima, and hence it corresponds to a computational phase transition. So in this sense, our results provide additional guidance to develop quantum neural networks, which are going to have really favorable landscapes. So if you have a polynomially large dynamical Lie algebra, you can reach overparametrization efficiently and not have barren plateaus. And those are already two aspects that are extremely desirable, because now we can train, we don't have barren plateaus, and we can reach the global optima with a exponentially fast in the overparametrization regime. Now, of course, the question becomes, how do we develop ansatzes with polynomially large DLA? Well, that is still an open question, and one that I invite people to continue exploring, to try to find how to develop quantum neural networks that are trainability aware using this algebraic theory. And finally, I just want to give a big shout out to some of my collaborators, because of course there's no person that is an island. Martin La Roca from Buenos Aires, Nathan Yu and Diego Garcia Martin from our quantum computing summer school, Kunal Sharma from the University of Maryland, and from Lanel, Gopi, Piotr, and Patrick, all collaborators from internal collaborators. And finally, one quick shameless plug. Some of you might know, every year we hold at Lanel a quantum computing summer school. The 2020 computer summer school, the application is going to go live in just a couple of weeks. So definitely stay tuned if you're interested in taking part in our summer school. You can check the Lanel website. We're going to advertise in Twitter, LinkedIn, etc. It's just going to be a couple of weeks. And we're currently actively seeking for postdoc candidates to join our group. So if you're interested, please send an email to Lucas, Cincio, or myself. And with that, I thank you very much for your attention, and stay safe. And thanks for staying so late on a Friday for everyone in Europe.
Amazing. Thank you, Marco. That was, yeah, very, very, very interesting, especially for me. I have lots of questions, but we can talk in private maybe. So Antal and Arusa, I think, will handle the questions. But yes, great talk. Thank you so much again.
Sure thing, yeah. Marco, thanks from my side as well. There was a question around when you were just introducing Barren Plateaus. It's more of a general question, but Yusuf was asking if Barren Plateaus are similar to the vanishing gradient problem in classical machine learning on one side, and then he was also curious about the curse of dimensionality and if it's there for quantum machine learning.
Right. So this is a question that I've asked myself quite a lot, like what is the relation between Barren Plateaus in classical machine learning and in quantum machine learning? So there are already some fundamental differences, because the vanishing gradients in classical machine learning is going to arise with the depth, whereas in most cases for quantum machine learning is going to arise with your width. And for instance, it's been shown that quantum neural networks can exhibit Barren plateaus even at already depth 1, like even without generating entanglement between your qubits. So in this case, Barren plateaus in quantum machine learning, for me, arise because you're living in an exponentially large Hilbert space. And for instance, you might be trying to compare two states that live in an exponentially large Hilbert space, and their usual overlap, or the expectation value of a state over a quantum over a Hermitian operator, might be exponentially small, right? So if you have two vectors and you're trying to compare them, their average overlap is going to be very small. Or for instance, if I have a very entangled state and I'm trying to do a local measurement, I have concentration of measurement results, which tell me that due to quantum correlations, I'm going to have a reduced state that is going to be very, very close to being maximally mixed. This is the original idea of Barren plateaus in the Google paper. So both of those are sort of not necessarily depending of the depth of your circuit, but more of your width and how many qubits I have, and the fact that I'm in this exponentially large Hilbert space. So while there are some similarities, I would say that it's not exactly the same as the vanishing gradients in classical machine learning. And regarding the curse of dimensionality, yeah, I've wondered the same. I'm actually not sure, and I would not dare to venture a definite answer to that. I think it's still an open question, like how much we can sort of fight a similar phenomena in QML.
All right, thank you. That was a really nice talk, a really good summary. I think it also connects a lot of the points that came out recently in your work, and some people are asking about if they're starting new in this, where can they study this? I think this talk is a really good summary to start and look at the references that you provided and go a bit deeper into that. So some people are asking more about the how everything is connected from going from ansatzes to parameters. So even like I would even ask that you said that so the parameters are generating or defining the unitaries, but which then define what states you can work with. So essentially, we could be working with a continuous or infinite set of parameters if it's defined on a continuous scale. So how do you then go towards the dimension of your Lie algebra?
So the thing about your parameters being continuous is not going to be a problem, right? Because you can think about like single qubit rotations. Those are continuous parameters, right? They live, they cycle between 0 and 2 pi, but in principle, they can be any real number. But what you need to study is how different values of those parameters transform into operators whenever I exponentiate the e to the minus I theta h, right? Yeah. So here, independently of the fact that your parameters are continuous, you still have a discrete number of parameters of each e to the minus I theta, right? And this is how the algebra just depends on the set of generators, because the Lie group tells you all the unitaries that can be generated by all the different continuous parameters that you can put into your ansatz. So the Lie group defines all the unitaries generated by all the possible continuous parameter choices that you put in there. So the Lie group is more fundamental because it's just telling you there is whatever you can generate by putting in your continuous set of parameters is going to be a unitary in your Lie group. And the Lie group is again just determined by what the generators are and not from the fact that your parameters are continuous.
But then we have another factor of the loss function. So does that mean that the loss function has to have certain properties, for example, 1-to-1, or it wouldn't work with any kind of loss function?
So that's the thing. Our definition of overparametrization pertains to the quantum Fisher information matrix, and the quantum Fisher information matrix does not take into account who your loss function is. It could happen, for instance, that you have some directions that you can explore in the parameter space that lead to the same cost function values. They do not change your cost function if I move in those directions. So I will always, the cost function, all that it can do is reduce the number of relevant directions. So, at most, if I can move in, 5 dimensions in parameter space, maybe 2 of them are trivial for the cost function, but I still get 3 relevant directions in my cost function, right? But ultimately, those 3 are upper bounded by 5. So this is why it's still interesting to look at the rank of the quantum feature information matrix, even if it's loss function independent.
Okay, so we should also like give attention to how we are designing the loss function.
Absolutely, yes, because you could get directions that, you know, are relevant in state space, but leave to like, you know, constant cost function values whenever you move over those directions. That is completely feasible.
Okay.
Sorry, I have to ask something just because you brought it up, but probably embarrass myself now. But doesn't the Fisher information change, you know, based on the where you are in the landscape? So like, how do you have this general definition? Is it through like I don't know, sampling parameters randomly, or do you include the optimizer, or how do you do
Right.
that?
So our definition of overparametrization is that the rank is saturated at least one point in the landscape. You know, and again, this definition, we discussed this, like should be like in most points in most points in the landscape, in one point in the landscape for most states in your data set. We just picked one definition because it seemed natural. And this is precisely why you can keep increasing the number of parameters, because maybe you reach maximum rank in one point, but not in another. But if I keep increasing parameters, I'm going to eventually reach maximum rank there. This is why, you know, there is an overparametrization onset, but keep increasing parameters might still help, because as you said, QFI matrix depends on what your set of parameters is.
Thank you. Antal, you want to go next?
Sure thing. There was another question which might or might not be related, but it was related to the role of initialization for variational parameters and how it's connected to Barren Plateaus. So could there perhaps be an oasis or a subspace in which the vanishing gradient is not a problem?
Right. So initialization strategies were probably the first solution to Barren Plateaus that were proposed. After the Google paper came out, the first one was, let's try to do a smart parameter initialization so that maybe we can start somewhere outside of the Barren Plateau regime. And in some cases, it's been shown to work. The problem is, how do we smartly initialize parameters is a non-trivial question, and it's extremely problem dependent. And what I've personally seen is that if in many cases, you might initialize around the local minima. And in that case, sure, you can initialize somewhere where you have gradients, but those are not going to be useful because I get out of this local minima into the Barren Plateau and I cannot find the global minima. So that's one of the interesting research directions for Barren Plateau, like how can we generalize good initialization strategies? In some cases they work, in some cases they get you to a local minima. It's definitely one of the top proposals. For me, the most important one is try to design ansatzes that do not have Barren Plateaus altogether, because ultimately smart parameters means that I'm in one region of the landscape and the landscape is flat, right? Because the landscape depends on your cost function and your ansatz. So maybe there is some region that has gradients, but ultimately, if you have a Barren Plateau, that means that most of it is going to be flat. So the best way would be to maybe have an ansatz that does not have a Barren Plateau altogether. And this is probably where at least my research is focused towards. How do we find features that are desirable for the ansatz design so that we will not have Barren Plateaus altogether?
Thank you. So maybe we take a couple more questions, Amira. Just let me know whenever. Yeah, we have some really good ones. So this one goes that provided that the observation that variance is inversely proportional to the size of Lie algebraic space, if it's correct, then can we say that quantum neural networks with polynomial size spaces are the way to go for QML? Are there any limitations to this?
Right. That is a fantastic question. That is a fantastic question, definitely. We're currently researching this. We just have some preliminary results saying they will not have Barren Plateaus, they will not be overparametrized. But that is not to say that, you know, they are definitely the way to go. We don't know what their limitations are. We barely started scratching the surface. Like, what our ansatz says, for instance, maybe you have a QNN that has a poly-size algebra. And let's say that you're trying to use it to classify like pictures of cats and dogs. It doesn't mean that it might work for that problem. So there's definitely limitations, because we don't know of a lot of ansatzes that are going to have poly-sized algebras. And it's not clear that the ones that we know of, like the one generated from the transverse field Ising model, is going to be practically useful, right? So this is more like a case study. but we've tried implementing that ansatz for some other practical applications, which is not finding the ground state of the transverse field-lighting model where it should work. And of course, it's not going to work, right? Because it's an ansatz made for a problem. So the question is, if we have a given problem, how can we reverse engineer it and define an ansatz that is polycized for that problem? That is still, again, an open question. And there are definitely limitations, and it's completely worth exploring them because we don't know. So this is why we're not claiming that they are the absolute best. We're just saying they have some favorable properties to them.
Okay, thank you. Should we take a last one, Anton?
Sure thing. Yeah. So let me just have a look quickly. There was a question related to the relation between overparametrization and the complexity of a ground state of the cost function. So yes, and the example that was brought is the ground state is an area law. Do you have any thoughts there?
Yes, absolutely. So again, I'm considering here cases wherever the ansatz that I'm using is sort of like a Hamiltonian Variational Ansatz or a QAOA type ansatz, where the Hamiltonian that you want to get the ground state of forms part of the ansatz. The ansatz is generated from that Hamiltonian, right? So in that case, it's obvious that more complex Hamiltonians are going to have more non-trivial terms to them, and their algebras might be larger. So, it's not for me, it's not a coincidence that the transverse field-lighting model has a polycized algebra, while this is like exactly solvable and whatnot. I'm pretty sure that studying the algebra of complex Hamiltonians that have complex ground states is going to lead to complicated algebras, right? And this is sort of what we found for like the spin glass. It seems to be like there are some fundamental limitations of what you can actually do easily, right? Nature is not going to give you a free lunch. So I definitely expect that finding solutions to hard problems is going to be hard. Absolutely.
Perfect. Awesome. Then maybe we can close now since we're already over time. Thank you everyone again for attending, and thanks Marco so much for this wonderful talk. It was really, really awesome to have you. And yes, then we will see everybody in January, so next year already. So thanks everybody, and thanks Marco again, and Francesco, Ilya, Antal, Arusa, thanks as always for helping to host. Have a nice evening.
Thank you very much. Have a great night.
Bye. Bye-bye. Thank you.
Bye.
Thank you. Bye-bye.